Hi, today we're going to do vector arithmetic, that's adding and scalar multiplication of vectors using component vectors. So component vectors allows us to add vectors without having to draw the arrows. We can do it numerically. Now, before we look into components, we need to look into what basis vectors are. So on the screen we have a definition. Basis vectors, they're a set of vectors that we can add and scalar multiply to reach anywhere in the 2D plane. So this is a definition that we'll take for our two-dimensional plane that we have here. So as an example, if I just had this vector here, which is just 1 in the x direction. Now, if I add this vector, I can add it as many times as I want, and I can travel as far as I want in this sort of x direction. I can add it and scale it in the negative direction, so I can go as far as I want in this direction, but there's no way that I can add and scale and multiply and get it going in this direction here. So this one vector that we have here would not be a set of basis vectors, because using that vector only, we can't add it and scale and multiply it to reach anywhere in the 2D plane. We're restricted to that line. Now, as it turns out, we can pick any vectors that we want to do this, just so long as they're not pointing in the same direction. So if I had another vector like this, then you could see for yourself with a bit of a play around, but you could add and scale and multiply those two vectors to end up anywhere in the two-dimensional plane. Now, the set of basis vectors that we conventionally use, because they're the easiest ones to do, are ones that are right angles and just go one magnitude in each direction along the x-axis and the y-axis. Why are they easy? Because they're 1 unit in length. It's very easy to do arithmetic with one. And they're right angles to each other, so it's very easy to add and subtract to go in both directions. So we give these two basis vectors special names. We call the one in the x direction, we call that the I vector, and we call the one in the y direction the j vector. So this being x and y, note alphabetical order, x, y, I, j. So that's one way to remember them to start off with. Now, these are, again, they're special vectors. They're 1 unit in length long. So they're our sort of basis unit vector. And I'll introduce you to this term now. Unit vector. This is a vector with magnitude of 1. Magnitude of 1. Now, as you'll see later, with unit vectors, we have a slightly different way that we show them. We put a little hat over the top of them like this to denote that they're unit vectors. So when we have the I and j, how we normally show that is we replace the dot and put a little hat. So that's our basis vector in the x direction, and our j vector is like that. That's our basis vector in the y direction. Now, why these vectors are so useful is we can represent any vector in terms of its basis vectors, or we call them, in this sense, a component vector, because the larger vector is made up of little components, which are in the form of these basis vectors. So again, I'll show you what I mean. If we draw a vector like this, okay? Let's call it vector A. A is made up of two lots of our I vector, so we can write A is two lots of our I vector and three lots of our j vector. So that's one way to write A, is where 2 in the x direction, 3 in the y direction, or 2i plus 3j. Another way to write it is how I've shown you previously, like this, where this shows how far it goes in the x direction, this shows how far it goes in the y direction. Now personally I prefer this notation at the bottom because there's less fiddling around to do with notation and you can sort of lose marks for that. So I prefer this notation down here, and sort of the worksheet series that I'm developing is shown in this format, but you do need to know both formats. Okay, so the great thing about representing vectors like this is that we can add them together very easily. So let's look at a couple of examples. Zoom out. Okay, so we've got 3 vectors over here, A, B, and C. If I wanted to add together A and B, again, I'll show you very quickly what that looked like using our old method. We'd go A, B is 4 across this way and 1 up, and then our A plus B would be this vector here. So A plus B is -3 and 3 up. Okay, now we can break these down into our component vectors and show it that way as well. So if we look at this A vector, that's one lot of I, the I vector, and it's 2 lots of the J vector up. If we look at the B vector, we've got another 1 lot of the J vector up, and we've got 1, 2, 3, 4 across in the negative direction. So if we wanted to add these things up using our components, we can say that our A vector, we're going +1 in the x direction, and then we are minusing 4, so we're ending up at -3 in the x direction. In the y direction, we are going up 2, and then we are adding another 1 to end up 3 in the y direction. So by adding the component vectors together, we end up with the same result as if we just add the vectors together, which should feel fairly intuitive because all we're doing is adding these vectors via the tip to tail method, right? Now, this way is a very long way of showing it, but we can do this whole process just using numbers. So if I write my A vector over here, A is 1 across and 2 up. My B vector is -4 across and 1 up. If I wanted to add A plus B, I can just show it like this. And then we just add the 2 x values and we add the 2 y values together. So 1 plus -4 is -3, 2 plus 1 is 3, and we're done with our problem. You don't need to go around with all the arrows anymore. Why this is really nice, if we had fractional components, so if this was say a half over here, it's a little bit difficult to show a half on this Cartesian plane because half isn't labeled, but numerically we're not going to lose anything there because we can keep track of everything. We're also not limited by the size of our Cartesian plane because we can make these numbers go as big as we want numerically. We don't need to physically show that. So I'll show you one more example. Let's do half B plus 2A. So again, our B can be written as -4, 1. Our A can be written as 1, 2. Now the way we're working with these is exactly the same as would work with matrices. You can times the half into each of these components. So we've got -2, 1/2 plus 2, 4. And then you're adding together the 2 there. So you can get 0, 4.5, which is 9 on 2. Or you could express it as 4.5. Okay, so that is our vector arithmetic using component vectors. I'll see you for the next video. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.